So let me share my screen again. Okay. Yeah, so brief introduction. If you don't know who I am, I'm Lynn Kaluzienski. I am a former postdoc at the University of Alaska Southeast. I did that for about 3 years. That ended last August. And I'm currently in between jobs, but still an affiliate and still continuing some work on the Taku Glacier. So today I'm going to be talking about Quonset or the Taku Glacier and some interesting findings that we have from there. This work is in collaboration with Jason Amundsen, Ian Jockin, Arlik Chang, and Shin Sugiyama. Those last two are from Hokkaido University. Okay, to give you a brief outline, I'm going to quickly go over some of the history of Taku Glacier. There's been a lot of work here over the decades, so we'll go through that. I'm going to also talk about our fieldwork campaigns that we've carried out from about 22 to 2025. So just giving you an idea of all the instrumentation we've done there. And a lot of the data hasn't been fully used, so it might be of interest to some people who are continuing to do research there. And then most of my talk is going to be actually about findings that have mostly come out of remote sensing. So this is a paper that should be coming out any day now. And yeah, so we will dive in. I'm sure most of you guys know where Taku Glacier is. It's the largest glacier feeding out of the Juneau ice field. This is just a photo from an airplane, just to give you a sense of scale. Currently, you have the Taku River flowing in front of it. You have this pretty large outwash plain that has a big tidal influence. And then most of our work has focused on the Piedmont lobe of the glacier, so the bottom portion. Briefly going into the history, we know back, this is mostly work from Roman Matika and Austin Post. Back in about 1750, we know that the Taku Glacier fully crossed over to Taku Point, blocked off the Taku River, created this glacial dam lake. So Taku Glacier is, or has been in the past, a tidewater glacier. We know that it rapidly retreated until about 1890, where it was all as far back as behind Brazier Hills. It had quite a bit of water and deep to about, I think this is, I forget if this is meters or feet. Sorry about that. So it had an active calving front around this time. I also want to point out the neighboring neighbor, Norris Glacier, had this huge outwash plain that sort of spread out into this area, and that's going to come into play later. So it was advancing. We have some photos from about 1990. Again, it had a calving front around this time. You can just barely see this outwash plain from Norris Glacier. We actually have photos from the Princess Sophia boat that was able to get in there and see some of the calving. So this is from about 1915. About 1937, the eastern portion is still calving, but that western portion is starting to come in contact with that outwash plain from Norris Glacier. So it's filling in with sediment as it's advancing. And then by 1980, it's created this Piedmont lobe. It's advanced past Brazier Hills and is no longer calving. And so you now have the Taku River out in front, and this outwash plain with lots of proglacial streams. So it advanced until about 2016 and has since been retreating. So for field work, we have, again, focused mostly on the Piedmont lobe. And in particular, one of our sites, or most of our work is upstream of what we call the landing strip. So this is where there's an actual place for uh, 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 helicopters land there and other things. To give you a sense of scale, this is a photo looking from Glacier downstream. You can see this large outwash plain. Tons of sediment has been deposited out in front. It's a really dynamic place. A lot of interesting proglacial features. So you can see these moraines that have formed over time. Each year, sometimes you have this ice kind of ramping up and over the moraines before retreating again. It's a really interesting place. Since its retreat, you often see areas of moats along the glacier edge, some lakes as well, so dammed in by some of um, the moraines that have formed. You also have a very dynamic proglacial area. So a lot of the sediment is constantly being rerouted with different uh, proglacial streams. Tons of sediment being deposited, moraines moving. You also have reforestation in certain areas. So it's really, really diverse area. Another really cool aspect is you can notice some of these rocks are really nice and smooth. These aren't, that effect isn't from the glacier. It's the fact that all of these rocks have been excavated from the bottom of Taku River as the glacier advanced. So you have these glacial erratics right next to these river formed or eroded rocks. So it's really, really cool area. And also there are some areas where the proglacial streams are quite big. They're non-crossable, and tons of water comes out during the summer season. We also have evidence for moraine failure. So if you see in the back of this photo, these aren't tiny trees. They're trees that have since, the bottom half of them have been buried because a moraine has failed and lots of outwash deposited all the sediment and just filled in this area. Okay. Again, briefly, I'm just going to go over some of the fieldwork that we carried out between 2022 and 2025 to give you an idea of some of the data that's there. We put out a series of ablation stakes. We put them in a centerline row, about 4 to 6, depending on which year. For that, we used a steam drill. And each season, we would go a handful of times throughout the summer. So 4 to 5 times if we were lucky. So we service those ablation stakes each of those times. Some of the years we were able to put GPS receivers out and service those on a near monthly basis. This past season, we put 2 out, one on the eastern side and one on the western side. I'll show you some data from that. One of the seasons when we went out with our colleagues from Hokkaido University, they brought their ground penetrating radar and we did quite a big GPR survey. Their particular radar system, you can change frequencies. And I think most of it was done at about 25 megahertz. That data is sort of a mixed bag in terms of what's usable. So we're still figuring out what to do with that data. This past season, one of our students, Arlick, put out an acoustic sensor. This was placed near that really large outlet stream with the idea of looking at the soundscape of diurnal patterns of outflow. So I haven't seen that data yet either, but it should be interesting. most of the data that we collected, or the focus of our work, was on photogrammetry from drones. And this is just to give you an idea of the scale. So on the left, we have a survey that we carried out at Mendenhall versus the right, which is just a portion of the Taku Glacier. So it's about 3 times as large as any of the surveys we'd done before, and would take a lot of time if we used a quadcopter. But in order to do this large of a survey, we relied on a fixed wing drone. This is the Wingtra drone. I wanted to go a little bit into detail just because I know a lot of people are trying to transition over to non-DJI drones. And so we've used this drone since 2022, and I had a very positive experience flying it, working with the company too. It's a Swedish company. 1 year we had the drone have a malfunction, and as it was landing, it crashed from about 6 feet, and it ended up there's some kind of jump in voltage that caused it. But we didn't even have insurance on the drone, and the company still replaced it for us because it wasn't user error. So really positive experience. This drone can it was able to survey this area in about 4 hours. So just very efficient, and can cover large spaces. This is the underside of it, so you can see where the camera is, and where the batteries are stored. This is a vertical takeoff drone, so it actually flies with that fin, and it'll land vertically as well. I do know we just did optical with it, but I've since seen that they have been trying to put other sensors on it, such as LiDAR and multispectral. I don't have any experience with that, but it does look like they're trying to have a more diverse set of sensors that you can use. One of the downsides, though, is portability. So you can actually put the drone in a backpack and walk around with it. The limiting factor is the batteries. So we would have a helicopter drop the drone off, but mainly the generator is the heavy thing that's not very mobile. So if you do want to use it in backpack mode, you're basically just limited by the amount of batteries that you have. But otherwise you can, it's not bad to transport at all. And this is the setup for the controller. It's just a touch screen. I didn't have any problems with that. And then this is the box that it comes in. But again, it comes with a backpack that is maneuverable. Okay, so going to some of the data that we have gotten from drone surveys, we were able to see a lot of interesting features. As the glacier has retreated, we've seen this moat formation on the western side of our array. You can also see smaller lakes that are forming in between the moraines that have formed in the past. We see evidence of, again, that moraine failure. So if you think back to the trees that were buried, that's from this moraine failure. So you can see the moraine on this side, and this side, I think, is from about 2015. And then when it failed, this entire area had tons of sediment deposited, and then since then there are more moraines forming on top. You can also see seasonal push moraines, some really interesting features where every year it advances and retreats, and you can see how the moraines migrate. This is some work that Jason's been working on, just putting together data from 2015 to 2024 just to look at variations in glacier retreat So in areas, for example, this is upstream of the landing strip. This really crevassed area has retreated a lot less than the western side of our array, where it's not as cracked. It's very has a shallow slope, and so you're getting more retreat. We also put together digital elevation models, and we're able to look at both thinning of the glacier, but also changes out front. So on the top, we have changes between 2023 and 2015. You can see that area where we had the moraine failure, we have about 3 meters of sediment deposited. Another aspect that shows up pretty well in these difference in DEMs is the just how dynamic the proglacial streams are. Every year they're migrating, so this is about a year difference, and you can see in one area a lot of the sediment is excavated, and in the other area it's filled in. And this is just a visual of how much it's retreated since 2015, so about 80 meters. Okay, so that's most of the field work that we've worked on. We're working on writing up some of those findings from the drone surveys, but again, we're still figuring out where exactly to put some of our data from the field. So for the rest of the talk, I'm going to focus on mostly remote sensing findings. And this is from a paper that, should be out any day now. So the focus for the remote sensing, again, is the Piedmont lobe area. And what sort of motivated this work is our student, Arlick. For her work, she was looking at its live data from the past, and she found something interesting. She looked at two different points, one on the west and one on the east, and found very different velocity signatures. And so I sort of dove into that. Originally, I thought maybe there's something wrong with the data, but have since found that that pattern holds. So I've looked through Sentinel data and TerraSRX data. This is an example of TerraSRX data over one calendar year. So this is from 2023. At the top, we have our temperature and precipitation. And on the bottom, we have velocity from the western side and the eastern side. So very something strange is happening. So the eastern side is acting as we would expect. So we would expect in the spring, when there's less melt, that the subglacial drainage would be distributed and there would be a lot of friction. So you would get an increase in velocity during that time period. Whereas in summer, when there's high melt, all of that meltwater is channelized to an efficient drainage system. The friction increases, and you have a drop in velocity during the summer. Something is happening on the west, where we have a very different pattern. You have slower velocities in the spring, and the velocities are increasing with temperature and precipitation, which we take as proxies for runoff. So a lot of this work has just been trying to put together data to look at this interesting signal and come up with some sort of explanation for why the West is behaving this way. So one of the first things I did was instead of just looking at two different points, I looked across a transect, and I also looked further in time. So this is Sentinel data going from 2017 to middle of 2025. And this is showing the velocity across this transect. And so this pattern holds every year. The east looks like it has higher velocities in the spring, and that shifts to the west by summer. We also found that in 2022, we had really high velocities that year. So just an interesting observation from 2022. Okay, so the next thing we wanted to do, see if I can, so after we recognized that the glacier, has this asynchronous seasonal velocity variation, we wanted to get a better idea of the timing and spatially, where does the peak velocity occur during the year, or when does it occur? So we applied a time series decomposition technique. So basically, we fit the velocity to a simple waveform of a cosine function. And so this is showing that the correlation between our modeled velocity versus on the top is Sentinel and TerraStar-X data. So this is for the western portion of our array, and on the bottom is the east. And so this fit actually worked really well in terms of capturing the peak in the peak timing of velocity, but it's not so good at capturing the amplitude, and that's because it's a simple function. It's gonna try to match for one overall amplitude, and it's not going to count for years such as 2022 when you have a really high amplitude for some reason. So we basically matched, did that velocity fit along every grid cell, and this allowed us to get a better spatial understanding of peak velocity. So the top plots are from Sentinel data, the bottom are for TerraStar-X, and our first plot is the day of peak speed. So again, this is looking at every grid cell. When in the year is it at its fastest? And we see that that pattern holds for most of the West peaks in July, whereas most of the East has those peak velocities in March. Another thing we were able to see is that there's a greater amplitude of oscillation on the western side. So the western side seems to be more sensitive to changes in water input. Okay. We also put out GPS receivers in 2025 in the same locations that I've been showing on that map. So one on the west and one on the east. We had them out between May and mid-August. And we were able to see that the same seasonal signal agrees with the satellite imagery, but we were able to look in better detail at diurnal signals, so on a much shorter time scale. So if we zoom into a particular week, we can see the diurnal signals of the west versus the east. In early summer, the diurnal variations were similar in magnitude across the terminus, but as summer progresses, those variations become larger on the western side. We also found consistently throughout our data that the eastern side lags the western side by about 2 hours. We also found, in terms of looking at the amplitude of the diurnal signals on the western side, we were able to kind of constrain the subglacial hydrology a bit. So we know that the western drainage system has to be efficient enough to route about 6 to 15 meters of surface melt. It has to be able to sustain, it has to be able to efficiently route that amount of meltwater to sustain the velocity variations that we're seeing. And it also needs to have a positive correlation between discharge and pressure.
Hey, Lynn, I think your slides might have stopped advancing.
Hmm.
I couldn't tell if you were trying to move forward, but we're on the Sentinel and Pterosaurus plot still.
Oh, which ones?
We've got A and B, green on the top, blue on the bottom.
Yeah. Um, I can see, yeah, I don't know. Okay, let me stop sharing and share again because I can see on your side that it's, yeah, I've advanced like 2 slides.
Okay, sorry.
Thanks for letting me know.
Perfect.
Okay, so, all right, so you guys were here.
Yes.
Okay. So this, yeah, I'll just go back a little bit because without the visual representations, you probably weren't understanding what I was talking about. So this is, again, using that waveform function, applying it to every grid cell. And the left two plots are the day of peak speed. So all the plots on the top are from Sentinel, and all the ones on the bottom are Pterosaur X. And this is, again, getting a really nice spatial understanding of where that anomaly is happening on the western side. And so that pattern holds where the western side has its peak speed in July, whereas on the eastern side, we see its peak speed occurs in March. And it seems like there's a pretty abrupt transition between the two sides in terms of where that's occurring. We're also able to spatially visualize the amplitude of oscillations and found that the western side has a greater amplitude of oscillations in general. Okay, so going back to the GPS data, again, we put out 2 GPS receivers in between May and mid-August, one on the west and one on the east. And then for this plot, I mostly wanted to look at a zoom in at the shorter time scale. So looking at diurnal signals over about a week example. So some of the main findings were the, yeah, so the diurnal variations were, sorry. Yeah, so they were of similar magnitude earlier in the season, and as summer progressed, that's when the western side has a much larger amplitude. It becomes pronounced over the season. Consistently, though, we did see a lag of about 2 hours of the diurnal signal on the eastern side. So the eastern hits its the western hits its peak a little bit later in the day. Also, from the amplitudes that we see in our diurnal signal, we can start to constrain the subglacial hydrological system on that side. So we know that the western side needs to efficiently route between 6 to 15 meters of surface melt in order to get the diurnal variations that we're seeing. And we also need a system that has a positive correlation between discharge and water pressure. So yes. So, and I'm advancing. Yes. Okay. So to get an idea of the hydrological system, we don't have any direct observations. One of the things I did was go back in time to some of the archival footage to maybe get a sense of what's happening beneath the glacier now because it's advanced over, we can see the terrain that it's advanced over. So this is a photo from 1969. Just showing a huge difference between the West and the East. I'm gonna, yeah, zoom into around the same time. These are from 1967. So the west, we're seeing uh, quite a large outwash plain. It's very shallow, um, a low slope of the terminus position. Whereas the eastern side has a much more jagged approach. It's no longer calving on this side at this point, um, but it seems like there's a lot less sediment out in front. It doesn't have that large outwash plain. And so fundamentally, there's some interesting differences between the east and west. If we go back even further, this is from 1948. Um, we can start to see a clearer picture. So around 1948, we still had a calving front on the eastern side, and we still had, you know, a deep sort of fjord in this area. Whereas the eastern side had this Norris Glacier outwash plain, right? So this is mostly outwash from the Norris Glacier when it was feeding in um, to the Taku and then retreating. And if we line that up with the location of peak speed, it correlates really well. So this leads us to believe that um, whatever's constraining the subglacial system, it has to do with this amount of sediment in this outwash plain. That's why this side is behaving differently. Okay, so the eastern side has variations that are characteristic of a drainage system that transitions from inefficient to efficient, whereas the western side has a drainage system that tracks air temperature and rainfall and has a positive correlation uh, between discharge and water pressure. And so this is sort of our my last slide. Um, all of our observations sort of point to fundamental differences in subglacial conditions at the front. Um, on the left side, or on the west, we have an inherited properties from the outwash plain that may influence the modern drainage system. I do want to point out that there could be differences in bed topography that contribute to the changes in velocity, but it does appear that the west has a shallower, flatter bed as a result, that the glacier was overriding this system, whereas the eastern side advanced through deeper water, so it likely has more pronounced topographic relief. It was also because it was in contact with the water longer, perhaps it built up less sediment in terms of creating moraine development. So we obviously don't have direct observations, but our hypothesis on what's causing these changes between the west and the east are is the potential for sediment-based canals. And this is work that is theoretical by Walder and Fowler and NG. So sediment-based canals are basically channels eroded into the sediment and then roofed by glacial ice. And theoretical work for these sediment-based canals have shown that they have the property that water pressure scales with discharge. So this is sort of where my paper leaves it as a potential hypothesis. Perhaps the western side has these sediment-based canals. There's a lot more sediment on that side, whereas the east perhaps there's more gravel or more bedrock. But one of the sort of conclusions of the paper is that we're hoping to get a better sense of the subglacial conditions, hoping for some seismic work. And so it just happens that that's exactly what Dougal's team was planning to do. They went out they had their first season last season, and they did seismic arrays on the west and eastern side. And so he's going to give a talk on all of his work. But it's really exciting that we have this hypothesis for this anomaly, and hopefully we might get an answer. Yeah, so with that, I'm not sure how much time I took with the um,
That's all right.
problems, but I'll leave it there.
All right. Thanks, Lynn. I think maybe we have time for one quick question or thought, and then we'll move on to Kaya to not get too far behind schedule. Anyone in the room or online?
I won't probably be more of a discussion. Lynn, hopefully you're able to stick around for the later discussion. You might not, but I definitely want to make sure we get your input for the white paper at the end because like your work's do a lot of tying things together too. So
Yes, so unfortunately, I can't stick around today. I meant to apologize for that at the very beginning. I'm excited that this is recorded because I'm really hoping to see a lot of the talks after. And I do plan to be involved on Wednesday. Or sorry, on Friday. But if there's anything in between now and then, feel free to reach out by email. And yeah, I'm looking forward to that.
awesome. Thanks, Lynn.
Awesome.
Awesome. All right.